All right, so today we're going to be talking about transformations of random variables. So we've talked about a bunch of different types of random variables, a bunch of different distributions. And now we're going to kind of really get to the heart of the course and start talking about transformations of random variables. And transformations of random variables is really an essential concept to probability and statistics generally, because a statistic is just a transformation or a function of a random variable. And so in order to do statistics, we really need to understand how random variables and their associated properties, their PDFs, CDFs, MGFs, etc., behave under transformations. So up to this point, we've looked at a random variable, say, let's call it x. And now we're going to look at some function of this random variable. And our function might be g of x. So we're going to work with a new random variable y that is a function g of x of our old random variable. So let's talk about what this notation means. Here, this function g is just a normal real valued function. It's function takes in a real number, spits out a real number. And to the extent that we can treat random variables, like a real valued variable, we could plug it in a function and get a new random variable, y. Of course, random variables aren't really just numbers, they're functions themselves. So what we really mean when we talk about g of x, where x is some random variable, is this new random variable y is the composition of g with x. So remember that our random variable x is really a function. X is a function from my sample space to the real numbers. And the new random variable y better be some other function from some sample space, let's call it s prime, to the real numbers. And so in order to get that properly in terms of functions, really what we mean when we plug x into g is that we're composing g with x. This is really a technicality that doesn't come up practically when we're working with random variables. Most of the time you treat them just as if they're real valued variables or they're numbers. But technically, we say g of x, we mean g composed of x. So why does that matter? If we calculate a probability, I want to calculate p of the probability that y is in A. So y is defined as g of x. I want to now take my transformed under this function g, variable y, and I want to find the probability it's in some set A, and here A is just some subset of the real numbers. I can calculate this as the probability that g of x is in my set A, if y is really defined as g of x is in my set A. And I can calculate this as the probability that g of x is in A. And using my rules, I can say that what we really mean, using my rules of what do we mean when we say a probability of random variables in a set, really we mean the inverse image of that random variable. So g of x inverse of A. And now I just have to remember from foundations what the rule is with the inverse image of a composition, and I can calculate this as the probability of when I do a composition of functions, it's really going to be the inverse of a composition. The inverse image of composition is I reverse the order. It's x inverse composed, and then I plug in g inverse, and then I plug in A. So this gives us a concrete way of calculating probabilities. The other way to think about this is if I want the probability that y is in some set A, I can calculate this as I know that y is g of x, so I can say, well, this is really g of x being in A, or this is the probability I can just multiply or apply the inverse image G here, and I can say this is the probability that X is in G inverse of A. Okay. So these are, we can call them the formalisms. Which will come up occasionally, but practically aren't always the most useful way to think about this. Typically, we just think about a transformation of a random variable as if treating the random variable as if it were just a real valued random variable. But technically, when we say g of x, by plugging in x into g here, really we mean opposing it, and that gives us, through a kind of a chain of equalities, that gives us a mathematically precise way of actually calculating the probabilities. This second one here is probably the most useful one to remember here, which is that if I want the probability that y is in A, that's, according to my definition, y is g of x in A, and I could always just apply g inverse on both sides. That would probability that x is in g inverse of A. And so actually, if I knew something about the probability that x is in sets, I could use that to calculate the probability of y being in sets. But the general game, and what we're going to talk about this lecture, is we're going to talk about, I know something about x. What can I infer about some transformation g of x? Okay. And we're going to talk today about all the different situations where, depending on what I know about x and what I know about g, what I can learn about g of x. And typically in this lecture, we're going to call g of x y. Okay. So let's look at some cases where, using our information about x and g, we can get some information about the transform version. So the first case we're going to look at is so let's see, the question is, how can I get the PMF of y from the PMF of x? Okay, so that's the question. How can you get the PMF of y from the PMF of x? So here, I'm saying PMF, so we're going to talk about the case where random variables are discrete. So y is going to be, or x is going to be discrete, and therefore y will also be discrete. And so I'm going to assume I have a discrete random variable x. So let's say one discrete x. And two, I know, and I'm going to say fx. Let's just leave it like that. F sub x, which is, this is the PMF of x. So the subscript x here is identifying that this is a PMF of little x. And three, what I'm going to want to get is, we're going to call f sub y. So want, and this is the PMF of y. Okay. So how do we do this? So let's look at how we derive the PMF of y. So notice that f sub y of some little y. So this is equal to the probability that y is equal to some value little y. That's how we define PMFs for discrete random variables. This is, using our definition of y, is the probability g of x is equal to little y. And I'm allowed to just apply my inverse function, my inverse image, g inverse to both sides. So this is the same thing as the probability that x is in g inverse of little y. So we should be careful here. This inverse here G inverse is the inverse image of G. And so it could be a set. That's why I write in, I don't write equals. It could be that there are more than one thing. So it could have the situation where if I look at my values, possible values of x and my possible values of y, it's possible, I have little y here, it's possible there are multiple x's, x1, x2, x3, that map under G to the same y here. And so if I look at the inverse image of this little y, it's actually going to be a set. So another way to read this is the probability that my transformation of x is equal to y is the same thing as saying the probability that x is in the set of things where when I put them in G, give me y. Okay, so that seems to make some sense. And we know from our dealings with PMFs that, so let's just say as an aside here, remember that the probability that some random variable x is in some set A, I can just sum my PMF for x over A. So I sum over all little x in A, and I sum my PMF f sub x. And that's this set here, this G inverse of y, is just some set. We call it A. So if you want, so what we get here is I could just sum over all little x now, and the set I'm going to sum over is the set G inverse of y, and I'm going to sum, I'm going to sum my PMF, f sub little x, or f sub x of little x, right? And we're done. What we've derived here is the theorem, in my discrete case, is that I got my PMF of y, f sub y of little y, is somehow related to the PMF of x. And that's exactly what I was looking to do. So I want my PMF of y. If I know the PMF of x, f of x, and I know something about G, enough to get the inverse image of G, all I have to do to get my PMF of y is apply this formula and say for each little y, or for each x in G inverse of little y, I sum up all those PMFs. And so this formula looks a bit scary, but it's actually relatively intuitive. All it's saying is if I want to find the probability that my random variable y is equal to some value little y, all I need to do is sum. The inverse image looks scary here, but it's just some notation. I'm going to sum over all x where g of x is equal to little y, and I'm going to sum up the corresponding, we can write it this way, we can sum up the corresponding probabilities that x is equal to that little value. So I want to know the probability y is equal to little y. I'm just going to sum up over all x where when I plug it into G, I get that little y. I'm going to sum up all those probabilities. So this is, we should put a box around this and call this is the intuition. The mathematical formalism here in this formulation is correct and a little more general, but these are saying the same thing. Let's look at an example. It's actually not so bad when we look at an example. So here's the example we're going to look at. Example. We're going to let x be a binomial random variable, and this binomial random variables have two parameters, n and p. N is the number of independent trials, p is the probability of success on each trial, and x, being binomial, is the number of successes. We talked about binomial random variables a bit so far, and we're going to let y be n minus x. So we can write it like that. Alternatively, you could say y is g of x. And here, g of x is just a function, n minus x. So this is written in the way we talked about it above, but we're just going to take the number of trials and we're going to subtract off x. So you can think about this. If x is the number of successes out of n, so x could be 0, 1, 2, 3, all the way up to n minus x, this is the number of failures. And so y is going to be the number of failures. If I probability p is success, I do n independent trials. What's the probability, or what's the number of failures I get? And that's just n minus number of successes I get. So what's the distribution of y? Well, what do we need? We're going to apply our formula that we learned above here. And so what I need to do is I need to figure out what this inverse image function, g inverse, looks like. And I need to know what my PDF looks like. Well, we've gone over the PDF before, so we know that. So let's just look at what the inverse function here. And actually, in this case, g is a one-to-one function. So the inverse image of g is just the typical functional inverse. So for one-to-one or invertible functions, the inverse image is more or less the same thing as just the normal function inverse, right? So if y is g of x is n minus x, we can solve for x. That tells us x is n minus y. So g inverse of y is just n minus y, right? So this is our side. We get g inverse. Okay. And from here, what I want to do is I want to get my PMF for y. I have x, I know it's binomial, I know what my function is. What is the distribution of y? Well, what's the PMF of y? So my formula says what I can do is I can sum over all x's in this inverse image of little y, and I'm going to sum the corresponding PMF at those values. And if x is in the inverse image of y, the inverse image of y, or the inverse here, is just n minus y. So this is just equal to x being equal to n minus y, and then we're going to sum the PMF at each of those x's. So we really don't need the summation notation. This is a bit overkill. We're summing over everything here. So all x's that are in this inverse image, well, there's only one x in there. It's n minus y. So we can just simply write this as f of n minus y. All right. The only x in this thing is the x equal to n minus y. So it's just f of n minus y. And right, so that introduces our y. We know this thing should depend on y. That introduces y there. Okay. So now we just need to plug in into our binomial PMF. So the aside is the binomial PMF. Fx of x would be n choose x, p to the x, 1 minus p to the n minus x. And so now we're just going to plug in n minus y for x. This is n, choose n minus y, p to the n minus y, 1 minus p to the n minus y. And we can do some simplifications here. So n choose n minus y is the same thing as n choose y. And I'll let you think about why that's true. Well, it's not that hard, right? N choose n minus y is n factorial over n minus y factorial n minus y factorial is equal to n minus y over y factorial, which is exactly equal to n choose y. All right. And, okay, this is still p to the n minus y. And we get 1 minus p, n minus y. We just get a y. Okay. If we were to call 1 minus p q, we could write this whole thing as n choose y, and we would get q to the y, and 1 minus q, which would be p, to the n minus y. Now that should look somewhat more familiar. This is the PMF of a binomial with parameters n, and instead of p we have q. So if you compare this, so we can compare, say, the form of this PMF to the form of this, instead of x we have y, and instead of p we have q. So it's a binomial nq. And so what we've shown is that fy of y is the PMF of a binomial n 1 minus p, q here is equal to 1 minus p. And so altogether this shows that y has a binomial n 1 minus p, or q, whatever you want to call it, distribution. And that's it. So that's a nice little application of our formula. It shows that if we originally have an x that is binomial, x counts the number of successes. If we look at the number of failures, that's also binomial, but instead of being binomial with a parameter p, it's binomial now with a parameter of 1 minus p. And I think that makes a lot of sense. So you can sit and think about why that makes some sense. But it's just flipping the definition of success and failure, you kind of get the same thing. Okay, so that's a nice little introduction. It shows us a simple case where in the discrete case we can get the PMF of something, of the random variable y, or transform y from the PMF of x. So now we're going to look at the continuous case. And so first we need to just give a couple definitions. So definition is a function is monotone if it is either increasing or decreasing. And, right, so an increasing function will look something like this. And for an increasing function, if I look at two values, a, where a is less than b, if this is increasing, then f of a will be less than f of b. Or if you want, sticking to our notation, g of a will be less than g of b. We're using g for our function. And the flip side is the decreasing function, of course, goes down like that. And if we look at some value a and b, where a is less than b, here g of a is going to be bigger than g of b, or g of b is less than g of a. So flip. And so we say something's monotone if it's either increasing or decreasing. So this is the decreasing case. One very nice property of a monotone function is that they're invertible. So all monotone functions are invertible. You can think about, if you go back to kind of high school definition of invertibility, you can do the kind of the line test where if you draw kind of a straight line through this, it only intersects the function once. So it's an invertible function. And that's going to be true of all monotone functions, so they're all invertible. So let's look at what we can say in the continuous case. And we're actually going to start with CDFs. So theorem. And we're going to say that if we have a random variable y as some function g of x, and I want to get the CDF of y is, and we're going to have two cases. In the first case, if G is increasing, then the CDF of y, we're going to say capital F of y, has some value little y. We can get that from the CDF of x, capital F sub x. And the way we get it is we plug in G inverse of y into the CDF for x. So real easy. If G is increasing, and we should put the condition that x is continuous, then if we want the CDF of y in the increasing case, we plug into the CDF of x G inverse of y. Super simple. And the other case is that if G is decreasing, we get a slightly more complicated formula. But if we want the CDF of y, we're going to have to look at 1 minus the CDF of x, evaluated at G inverse of y. Okay, so that's the formula. Where does it come from? It's actually, you can do this with a nice little picture proof, as it were. But where this formula comes from. So, case 1, say case 1 proof is that, so G is increasing, and what I could do is I could plot x, and I could plot it against my values for y. And there'd be some function G, right? It's a monotone function, so and it's increasing actually, so it has to look something like this. This is G of x, and this gives me y. So that's my line, G of x, y is G of x. And if I want to look at the f of y of little y is the probability that my random variable y is less than or equal to little y. Or I could write it as a probability that random variable y is in this interval negative infinity to little y. So I could write it like that. And so if I mark that value little y on my y-axis, and I look at the kind of set of all things less than or equal to that on my y-axis, that would give me that kind of set. And if I extend my little y over to my function, so there's going to be some value over here that when I plug it into my function gives me y. What's that value? That value is exactly G inverse of y. If I plug G inverse of y into G, it gives me back y. G of G inverse of y gives me y. And so if we look, if my random variable is in this set here, that must correspond to the fact that on the x-axis, I'm in this corresponding set here, or I'm less than or equal to G inverse of y. So I'm going to argue that this is the same thing as the probability that x is in the set negative infinity to G inverse of y, like that. And I don't have to worry about G inverse being potentially set because my function is increasing and hence invertible. So this G inverse is a true inverse. So my argument is that the probability that y is in this set here, if I were to, corresponds to the probability that x is in the set negative infinity to G inverse of y, right? Or alternatively, if x is in the set, when I map it in G, then y must be in this set here. And this, of course, is just f(x) of G inverse of y, and that's exactly what I claimed in my theorem. So that's the increasing case proof, and we could do case 2, which is very similar, which is decreasing. And so I'll go through it real fast. Here's my plot. Here's x. Here's y. Now I have a decreasing function that looks something like that. This is G of x, gives me y. If I want to find f(y) of y, this is the probability that y is less than or equal to little y. So if I were to mark my little y here, that is the probability I'm kind of in this set. I'm marking off on the y-axis. If I look at which values of x map into this set on the y-axis, that's everything bigger than this value here, which is exactly g inverse of x. So the set of values that map into being less than or equal to my little y value here is all these values here bigger than g inverse of x. So this is the probability that x is bigger than or equal to g inverse of x. G inverse of little y. Sorry, this would be g inverse of little y. So this is probability g inverse of y. Oops, sorry, little y. And that's 1 minus the probability that x is less than or equal to g inverse of y, which is 1 minus the CDF of x at g inverse of y. And that is exactly my second case of my theorem. Which tells me I need the 1 minus in there. So that gives me this case, and the increasing case is really simple. So that's a little proof. Let's look at a fun example. So let's look at the example. So here's the example. I'm going to say x is distributed uniformly, continuously, and uniformly, right? So we're talking this is a continuous case. Uniformly, continuously, 0 to 1. So if I look at my PDF, 0 to 1, here's my PDF. Looks like that. It looks like 1 inside, 0 to 1, and 0 outside. And the corresponding CDF, 0 to 1, starts off at 0. It increases up to 1, and then flattens off at 1. So this is my CDF. So this is my CDF, and this is my PDF. So this is for x. Let's say of x. And what I'm going to do is I'm going to look at, let's define y to be negative log of x. Now that's a strange transformation. And so equivalently in this case, my g of x is negative log of x, right? So what is the CDF? What's the CDF of y? Now, if you didn't know the theorem above, this would be a really hard problem. Give you x, it's uniformly distributed, and I give you negative log of x. Well, how would you come up with the CDF? Luckily, we have this theorem, and so it's actually quite straightforward to apply. The CDF of y, fy of y, which case are we in? This is a decreasing function. Negative log of x. So log of x looks like this. And so if we take the negative of that, this is negative log of x. And so fy of y in the decreasing case, we can take 1 minus our CDF of x, and we can plug in g inverse of y. Okay, so we derived the CDF of x above. That was this one here. And so we need g inverse of y. So let's just, as an aside, let's say that if y is negative log of x, we can move the negative over. Negative y is log, is log of x. X is e to the negative y. And so this is g inverse of y, right? So we solve for the inverse function. That gives us g inverse of y. And so this is 1 minus CDF of x at e to the negative y. And we can argue that for y bigger than 0, e to the negative y is between 0 and 1. Certainly it's positive, and it's 1 over e to some power. So it's actually, and we're never going to get something that's smaller than 1. And if we look at our CDF of f, so this is fx of x, between 0 and 1, our CDF, that's supposed to be a straight line. Let's redraw that. It's supposed to be just a straight line. The formula is fx of x is just x for x between 0 and 1. And you can go back to the lecture on the uniform distribution, and between 0 and 1, it's just a straight line with slope 1. And so, coming back to here, fx of x is just the identity function. So it's just 1 minus e to the y. And that's it. So what we showed is that fy of y is 1 minus e to the negative y. Okay. So that's the CDF. Now, if you're clever, you're going to notice this is the CDF of exponential distribution with rate parameter 1. And so if the CDF of y is the CDF of an exponential with rate parameter 1, then y better be distributed as exponential with a rate parameter 1. So I guess the answer to the question is that's the CDF. The kind of more full answer is, yeah, it's an exponential 1 distribution. So if I have x that's uniform, and I take negative log of x, that has a standard exponential, is what it's called, the rate parameter 1. So that's the theorem for CDFs for continuous. And in the discrete case, we were able to get a formula for the PMF. And so let's say, what about the now in the continuous case, the PDF? If I have a continuous random variable, and I know it's PDF, and I look at some function of that random variable, can I get the PDF of that function? So here's the setup for the theorem. Y is g of x, and what we're going to assume is that 1, x is continuous. 2, g is continuous. And monotone. And furthermore, g inverse, if we know it's monotone, it has to have an inverse. Monotone functions are all invertible, so g inverse will exist, is continuously differentiable. So it's differentiable and its derivative is continuous. So that's called continuously differentiable. So in the discrete case, if we go way back up in our notes to the discrete case, we were able to we kind of just had this general theorem that said, okay, look, if I have a random variable x that's discrete and I know f of x, I can get the PMF of f of y. No real conditions on that theorem. In the continuous case, things are more complicated, and there are a couple conditions on our theorem. So x is continuous, the function is continuous and monotone, either increasing or decreasing, and its inverse is not only continuous, but continuously differentiable. Its first derivative is differentiable. If those things are true, then we have a general theorem that we can apply. And the theorem is, if I want to get the PDF of y, fy of y, I can derive that from the PDF for x. So in the discrete case, it looks something like fx of g inverse of y. But now in the continuous case, I have to multiply by the derivative of g inverse with respect to y. And I have to throw absolute values on that. So this is the formula to remember. It is basically the change of variables formula from Calc 3. It says that the PDF, or the density, of y is the density of x evaluated the inverse, but I have to multiply by the absolute value of the derivative of this inverse. And that absolute value of that derivative basically tells me how much does my function g stretch or squish my space. Their derivatives are rate of changes. They're kind of how much do I deform the space. And so when I go from x to y, I deform the space in some way with g. I stretch it, I squish it in some way, and at each point I do it to various degrees, and that can be measured by the derivative, and so I have to account for that. And so the density of y, fy, is related to the density of x, but I have to account for how much I'm stretching and squishing the space in the various points. So this is the formula, and this is true for all little y that are in capital Y, and here capital Y is the support of my random variable y. It's 0 elsewhere. So implied in this is that my PDF of y is 0 outside the support of y, right? And that's the kind of general case we use. Okay. So it looks a bit intimidating at first, but it's not that bad. It's just it's f of x evaluate the inverse, but then it's just multiplied by the derivative, or the absolute value of that derivative. So let's look at where this formula comes from. So let's look at a proof of this. So first case, again, we're going to look at where g is increasing. And if g is increasing, and I want my PDF of y at little y, so this is fy at little y, I know that I could take a derivative of the CDF of y, right? So I could say, well, what's the CDF? CDF of y, if I take a derivative, I get the PDF, right? That's our known relationship for any random variable, and so it's true of y. Well, I have a formula for how the CDF of y is related to the CDF of x, and that's why we did the CDFs first. The CDF of y is related to the CDF of x. It's fx at g inverse of y if g is an increasing function, right? And that's just what we did. And so my PMF, or PDF of y, is a derivative of this thing with respect to y. And so we have to apply the chain rule. By the chain rule, I take the derivative of the outside function, which is little fx, and I leave the inside alone. And then I multiply by the derivative of the inside, which is the derivative of g inverse dy. So if we compare that to the above formula here, it looks really similar to it. No absolute values. Well, we don't need absolute values in this case because this thing here is bigger than 0. It's an increasing function, and so the inverse here will have a positive derivative. And, okay, let's look at case 2. Bet you can know where this is going, where g is decreasing. We can say that f y of y is ddy of f of the CDF. And our formula is a little bit different in this case. In the decreasing case, we said that it's 1 minus fx g inverse of y. But that doesn't pose much of a problem. We can still do derivatives. We get negative fx g inverse of y. And then we have to take a derivative of the inside here. So we get d g inverse dy. Now when g is decreasing, this thing is less than 0. And so if we multiply by the negative there, we could move that negative. And if we multiply that thing that's negative by -1, that's the same thing as just taking the absolute value, right? If you have -5 times -1 is 5, that's the absolute value of -5. And similar in the increasing case, absolute value of something positive is equal to it, so we can throw absolute value bars without too much worry. Now these two formulas are actually the same, and they match the formula I gave above. So they match the formula in our theorem here. And so you see now where the absolute value bars come from, and the derivative just comes from the chain rule. basically. So this derivative here is chain rule. And so we have a couple more conditions in the case of continuous random variables. We want to get the PDF. We need this thing to be differentiable because ultimately we need to be able to take the derivative of G inverse. We need the absolute value of the derivative of G inverse. So that thing better be differentiable. So unfortunately we have that condition, which we don't in the discrete case and we didn't have for the CDF theorem, but we do for the PDF theorem. Okay, so let's look at this thing in practice. So in practice, here's our example. I'm going to look at x, and x is going to be distributed with a gamma distribution, which we talked about. And it's going to have two parameters. Typically, they denote alpha beta. Here I'm going to say n beta, and here n is an integer. I'm allowed to say n is an integer. More generally, gamma can have some parameter alpha. It's not an integer, but we can let n be an integer. The reason we want to have n be an integer is because gamma of n, if n is an integer, is just n minus 1 factorial. If you remember from our definition of the gamma function. And so in this case, our PDF of x, fx of x, is 1 over n minus 1 factorial, beta to the n, and we get x to the n minus 1, and we get e to the negative x over beta. Okay. So this is, go back, this is true for x bigger than 0. And if we go back to our definition of the gamma distribution, we see that this is exactly what we get if n is an integer. Instead of gamma of n, we get n minus 1 factorial. And let's look at what happens if we invert x. So consider y to be equal to 1 over x. Okay. And so equivalently, this is saying that g of x, that g of x is equal to 1 over the lex. Okay. So what happens if we invert? Now, we have to check that this adheres to our theorem, right? Our theorem says that we have to say that G is monotone, and we have to say that G inverse is continuously differentiable. Okay. And it is, right? 1 over x is certainly monotone, and if we get the inverse function here, so what's the inverse function? If y is equal to 1 over x, then equivalently x is equal to 1 over y. So this is the inverse function, g inverse of y. And so the derivative, d dy of g inverse, is equal to, well, it's the derivative of 1 over y. It's negative 1 over y squared. All right, that thing is differentiable. It's also continuous. So using our theorem now, let's look. Our theorem says that if I want to get the PMF or PDF of y, fy of y, I can look at the PDF of x, I plug in g inverse of y, and I multiply by the derivative, dy, so something like that, right? And we now kind of have all the parts here. G inverse, so this is, let's just write this out in a couple steps. G inverse of y is 1 over y. the derivative of g inverse is negative 1 over y squared, absolute value bars. And now I got to remember what fx is. We derived that above here, so let's go back up. Here's fx. And so I'll just plug in for what fx is. We have n minus 1 factorial on the bottom, a beta to the n. And then instead of x, we're plugging in 1 minus 1 over y. And that is to the n minus 1. And we get e to the negative. Instead of x over beta, it's 1 over y over beta. So 1 over y beta. And then I have the absolute value of 1 over y squared, which I can just write as 1 over y squared. Okay. We can simplify it a little bit more. We can combine the 1 over y here with the 1 over y squared here. So it's 1 over y to the n minus 1 over 1 over y squared. So simplifying it, we get n minus 1 factorial, beta to the n. And if we combine those y terms, that's 1 over y to the n plus 1 now. Because this is like y. This is like 1 over y. Oop. This is the same thing as, well, let's not delete it. This is the same thing as 1 over y. Squared, right? So I can add the 2 onto this boy and get n plus 1. And we have our e to the negative 1 over y beta. And this is true for y bigger than 0. How did they get the support for this? Well, the support is actually not that bad. If x is bigger than 0, then 1 over x is also bigger than 0, and this thing is y. So we know by support is also y also bigger than 0. But this is my PDF. And at that point, you may not recognize it as anything. You know, in fact, no one will probably recognize this as a known. But it is a PMF. It doesn't necessarily have to have a name. It's just some PMF. Not every PMF has a name. Not every distribution has a name. It's a valid PMF. We can check that. As it turns out, in this case, it does have a name. But a name of a distribution isn't that important. You could say that, in this case, y is distributed inverse gamma with parameters n and beta. So, not surprisingly, the distribution with this as its PDF is called the inverse gamma function, or inverse gamma distribution. Well, because it's the distribution you get if you take 1 over a gamma random variable. But in general, you don't have to necessarily get something you recognize. Typically in the examples, I'll try to get something that's kind of nice and recognizable, but it may just be what it is, and that's the PDF. Okay, so this is how we deal with things in the continuous case. We have a couple conditions. We need the function g to be monotone, and we need the function g to have a continuously differentiable inverse. And so a kind of immediate question here is, what happens if I want to do a transformation that's not monotone? We didn't run into that problem getting the PMF in the discrete case. And so is there some way around that in the continuous case? And the answer is yeah, kinda. As long as the function g is monotone kind of in segments, you make it into a bunch of segments, and each of those segments is monotone, you can derive a similar kind of theorem. So let's look at that. So what if g isn't monotone? And so the answer is okay, as long as we can segment g into monotone chunks. So what do I mean by that? So my example here is, what if I look at y is the square of x? Now that, depending on x, might not be monotone. It's certainly not monotone on the whole real line, right? So if I look at my values x and I look at y, and this is, you know, it's supposed to be kind of similar to 0, like that. This is y is x squared, and this is not monotone. Not monotone. And so my theorem really isn't directly applicable. However, if we break it into two chunks, if we look at just this part of it, let's call this as g1 of x, this is monotone on 0 to infinity. It's increasing. And if we look at this other chunk here, we can call this g2 of x. This thing is monotone, now decreasing, on negative infinity to 0. So we're actually going to we're going to derive a very similar theorem, or we're going to state a very similar theorem for cases like this where, well, the function overall isn't monotone, but I can break it. I can just say break it at 0, break it at some points, and as long as on each of these kind of segments it's monotone, we can apply the theorem to each of the segments and kind of recombine at the end. And so everything will work out okay. So this theorem, it's a bit to write down, but let's write it down, and then we'll look at a real nice example of when this is useful. So let's write down the theorem. Here's the theorem. So let's call this piecewise monotone transformation. Okay, piecewise monotone transformation. So what do we want to say? X is continuous and has support, let's say fancy x, so that's fancy's cursive x is our support of x, and let a1, a2, all the way up to ak partition the support of x. So the picture is, here's my support of x, and I'm going to break it up into a chunk, a1, a2, a3, etc., all the way up to some a sub capital K. And what we want to say is that we're going to let g sub I be the function g on each of the chunk a sub I, and I here goes 1 to capital K. So if this were my function, let's draw this so it actually conforms correctly. It goes like this, maybe it goes like this, goes like this, and then it goes like this, and then it goes like that, right? So it's monotone. On each of the chunks, it's monotone. It's either decreasing or it's increasing. And we're going to call this chunk here G1, this chunk here G2, this chunk here G3, etc., this chunk here GK. And let's say if each of these G sub I satisfy the conditions of the previous theorem, they're monotone on their chunks, let's say on a sub I, right? And they have an inverse, and the inverse is differentiable and continuous. So that's condition 1, if each of these satisfies conditions, and 2, if the image of a I under gi is the support of y, which say it's just some capital Y. So this is a little bit more of a technical condition, just basically says that each of these g sub I, if I map to the same set y, so if I plug in a sub I into g sub I, it gives me the same set y. We'll call that set y the support. Typically that's going to be the case. So typically that's not the one to check. Typically the one to check is this, that they all kind of, you can break up your function into a series of monotone functions. Okay. So basically, the statement of the theorem is a bit wordy, but it says you can break our thing up into chunks here. So we partition our support of x, and these g sub I satisfy the previous theorem on each of my chunks. they're monotone, invertible, and the inverse has a continuous derivative. Then I basically have something that looks a lot like the previous theorem, where I can get now, let's say, so y is g of x, and g is this overall function that's monotone only chunk-wise, but I can still get the p df of y. But now what I'm just going to do is I'm going to sum over all the chunks. K goes 1 to k, right? These are my chunks, a1 to ak. I'm just going to sum basically what we had in the previous theorem. I'm going to plug g inverse of y into fx, and then I'm going to multiply now. I'm sorry, plug gi inverse of y into fx, and then I'm going to multiply by the derivative of gi inverse dy, and with some absolute values. So it looks almost identical to the previous theorem, but now I have k things that I'm summing up here, corresponding to k chunks, and so I kind of apply the theorem to each of the chunks, and then I just sum up. And so this is the PDF of y as log for all the values in this support, this common image y, and a 0 outside of that. Okay. A bit more complicated of theorem, and it would be very complicated if you applied to very complicated functions, and one could, but let's look at the simplest case, and the simplest case is where we're just going to have 2 chunks. And so let's look at how this gets applied. So example here is our chi-squared random variable. So if we have x, and x is a standard normal, so we go back to your normal, think about standard normal. Standard normal is 0 mean unit variance. And I'm going to define y as the square of x squared. So g of x in this case is x squared. We say that y has a chi-squared distribution with 1 degree of freedom. We write that capital chi with the square and parentheses 1. The 1 is degrees of freedom. In this case, degrees of freedom is 1. So the square, it's basically the square of a normal is called the chi-squared with 1 degree of freedom. So let's take draw a little picture of what their transformation looks like, right? So here is x, here is y, here's our transformation. Y is x squared. Now this thing is not monotone, right? So this whole thing is the support of x is equal to negative infinity to infinity. It's the whole real line, right? Normal random variables have an infinite support of the whole real line. And so if I look at the square of that, that's x squared is not a monotone function on that support. But it is monotone if we break it here. So let's say a1 is just the set 0 to infinity, and a2 is the chunk negative infinity to 0. Don't really have to care if I include 0 or not. It's a continuous random variable. Any individual point won't contribute any probability, so include it in one or the other or none. Doesn't really matter. On each of these 2 chunks, I'm going to define my 2 functions. So on a1, I define g1 of x, which is x squared. And on a2, I define g2 of x, which is also x squared. Okay. And my support of y, capital Y here, capital Y, is positive numbers, right? 0 to infinity, right? If I take something, any real number in x square, it's going to be something that's positive, okay? Or at least non-negative. And notice that if I were to take some value little y here, it could have come from one of 2 values. It could have come from square root of y, or it could have come from the negative square root of y, right? So if I had plugged square root of y into my function, I would have gotten y. If I had plugged negative square root of y in my function, I would have gotten y. So, right, this thing's not invertible. And So what this means is that my two functions are going to have different inverses. So let's just write this all out. A1 is 0 to infinity. G1 of x is x squared. And G1 inverse of x, G1 inverse of what typically we write y, is the square root of y, right? If I were to solve y is G1 of x is x squared, okay? If we know on 0 to infinity that x is positive, or that y is, that x is positive, then it must have been, the inverse must be square root. The alternative is that if we're on, we are on the set negative infinity to 0, g2 of x is still x squared, but g2 inverse of y is now negative root y. So the inverses are different here. So this is where we're going to see some difference in this problem, right? On this part, a1, the inverse of x squared is just x squared, or is just square root of x. And on this chunk, a2, the inverse is negative square root. Okay. Just to keep, we got to keep these things all straight. The other quantities we'll need is we need to calculate the derivatives. So if I look at, given our formula, if we go back up to our formula, right, we need not only g sub I, but we need the derivative of the inverse with respect to y. So if we look at dg1 inverse dy, g1 inverse is root y, derivative of root y is 1 over 2 root y, and dg2 inverse dy is, just a negative sign up front, so it's negative 1 over root 2, or 1 over 2 root y. But now we're basically ready. All we need to do is recall what the PDF is for a standard normal. The PDF for a standard normal is 1 over root 2 pi, no sigma squared is 1, exponential, negative 1/2, no sigma squared, because sigma squared is 1, and x minus mu, but mu is 0, so it's just x squared. And this is true for any value x. So our PDF here of fx is 1 over root 2 pi, exponential of negative 1/2 x squared. So I think we have all the ingredients now. We have g1, g1 inverse, g2 inverse, derivatives of those, and we have fx. And I think at this point, if we go back to our formula, we need fx, g1 inverse, g2 inverse, derivative g1 inverse, derivative g2 inverse. So we're ready to apply the formula. From here, it's pretty simple. The PDF of y, the PDF of x squared, the PDF of y, is, well, I sum over my two chunks. So I have little k goes 1, 2. Well, capital K is just 2. Okay, so it's sum two things. Segmentation is maybe a bit overkill, but in any case, I plug its fx of g, use k here. So we can use I. Let's just change this to I. I guess I should change that my formula above here, because that's slightly incorrect, right? If I use k, let's just use I here, right? I goes 1, so this g sub I, right? Okay, that makes more sense now. Okay, so this is sum I goes 1 to 2, gi inverse of y, derivative gi inverse dy, absolute value bars. Only two things, so this is fx g1 inverse of y, dg1 inverse dy, and then in the case where I is 2, goes fx g2 inverse of y, dg2 inverse dy. Okay, and we basically have all the parts now, right? So this first thing is, what's fx? It's root 2 pi. G1 inverse is square root, so exp negative 1/2 square root y squared, and the derivative is 1 over 2 root y, And then for our second part, if we can squeeze it in here, it's still fx is 1 over 2 pi exp negative 1/2. Now we have g2 inverse is negative root y. Square that, and we multiply by negative 1 over 2 root y. Oh. Okay. Negative 1 over 2 root y. So let's see if we can simplify this. 2 pi, 1 over root 2 pi, exp, negative 1/2. Square root of y squared should be absolute value of y. But we know here that y has to be bigger than 0. We don't really care if y is less than 0. That's not in the support of y. If you take something and you square it, y is x squared, right? So y is better to be positive. And so we actually don't need the absolute values. This is just y. And again, we don't need the absolute values. So just like that. And you get 1 over root 2 pi, exp, negative 1/2. And again, we just get a y. And absolute values now just get rid of negative 1 here. So we have 2 root y and 1 over that. And these are identical. And so we actually can say it's 2 times one of them, and we can cancel one of these 2's. So we could just say it's 1 over root 2 pi, exp, negative 1/2 y, 1 over root y. And so that is what we get. And this is the PDF of a chi-squared distribution on 1 degree of freedom, i.e. if y is x squared, where x has a standard normal distribution. That gives us what we call a chi-squared, and that's the PDF of it. It's not too nice. It is actually a special case of the gamma distribution. So if you're clever, you can figure out what parameters. The 2 pi may throw you a bit, but it's a specific case of a gamma distribution. But we call it chi-squared because it's a very important distribution. Comes up all the time. You've probably heard the term in an intro stats course. Okay, so the last transformation thing we want to talk about in the last couple of minutes here is a more fun one. It's called the theorem is called the probability integral transformation. And what it says is that if x has CDF, say capital F sub x, and x is continuous, and if f is continuous, so is fx, then if we look at define a random variable y to be f sub x of x. So what does that even mean, right? Normally I write y as some g of x. Well, I'm allowed to choose whatever function g I want. What if I choose g as the CDF? The CDF is just a real valued function. I'm allowed to choose it. And so I'm allowed to plug the random variable x into its own CDF. Seems a bit strange. If I do that, my resultant random variable y is uniformly distributed. And that's kind of an amazing fact, and a very useful fact. So let's look at a little proof of it. Basically says, look, if I plug a random variable into its own CDF, it is always uniformly distributed. So let's look at the proof. We know that we can assume that fx is, now typically we say all CDFs have to be increasing. This short version of the proof, we're going to say that f has to be strictly increasing. It can't be monotone. It can't be flat at any point. If it's strictly, they're always increasing, and there is a proof version where we don't talk about strictly increasing. If it's strictly increasing, then fx is invertible. So fx inverse exists. Okay. If fx inverse exists, then we can play the following game. Okay, so what we want to say is y, our random variable, is fx of x, and we could write this as g of x, where our function g is just fx and is invertible. The CDF of y, we have a theorem for what the CDF is in this continuous case. The CDF of y, fy of y, we have a increasing function, and we're looking at g of x. So the CDF of y, we know, is the CDF of x, and then we plug in g inverse of little y here, right? That's just our theorem from way far above. If I want this just generally, if I want this for a continuous random variable, if I want the CDF of y, I can take the CDF of x and plug in g inverse of y. But now we chose this g very specifically so that it is fx, and so g inverse is fx inverse, and so we get fx of fx inverse. Those cancel, and we get y. That shows that the CDF of y is just y. Why does that help us? Because the uniform, recall, the CDF for a uniform random variable between 0 and 1, if we looked at fx, it would, let's not say x, let's say if we have u and u is distributed uniform between 0 and 1, f of u, so here's a random variable u, was basically 0 if u is less than 0, 1 if u is greater than 1, and just u if u is between 0 and 1, right? And this is the case we care about. So look, the CDF of a uniform random variable is basically just the variable. It's just the identity function. Fu is just u. Fy is y. And so this gives us the CDF of a uniform 0, 1. Now technically I'd have to show that these other two cases also match, but they're very simple to show. And you can think about how you would show those. But the main point is that the kind of part where the action is the same. This then gives us that the CDF of y is the CDF of a uniform 0, 1, and so y, which is, recall, as if I plug x into its own CDF, has to have a standard uniform distribution. And that was a theorem. That if I plug x into its own CDF, I get a uniform distribution. So why did I say this is a useful theorem? This is useful for generating data, generating random variables computationally. So this is just kind of a little fun aside, not something you necessarily need to know for the final. But let's say generating random variables. Okay. What I want is a random variable with a CDF, let's say fx. So I want x, a random variable with a CDF fx. Specify whatever I want. I want a normal random variable. I want an exponential random variable. And so these I know what a CDF is, and I want to be able to generate numbers from this distribution. What I know is that if I were to take the random variables, if I want to be able to generate values from x, if I were to take that x, so I'm going to generate some numbers from a uniform distribution, from a normal distribution, from a chi-squared, from whatever distribution. If I were to take those numbers as x's and I were to plug them in the CDF, I would get a bunch of other numbers. So the CDF is just a function I know. So I could generate a bunch of exponential things from random variables. If I were to plug them in their own CDF, I would get a bunch of numbers that would follow a uniform 0, 1 distribution. And so if I look at f inverse, fx inverse of those uniforms, I would get fx inverse of fx of x, which is just x. And that would follow, this thing would have the CDF I want. It would have the distribution I want. So here's my algorithm. 1, generate y following a uniform distribution. 2, plug y into desired CDF. If I want a normal random variable, I plug them into the normal CDF. If I want an exponential distribution, I plug those y in the exponential distribution. If I plug into the inverse of the desired CDF, so I want exponential, I plug into the inverse of the exponential CDF. Normal, I plug in the inverse of the normal CDF. If I plug those uniform into the inverse of that CDF I desire, I will get, according to my theorem, my probability integral transformation, according to this, I will get some things. X equals fx inverse of y will be distributed as I want. And so that is actually how a lot of different random variables are generated on a computer. First, you come up with a really clever algorithm to generate uniform 0, 1 random variables. After that, for whatever kind of other random variables I want, if I can get the inverse CDF, I can just generate things from a uniform, plug them in the inverse CDF, and I get the random variables I want. And so you can generate a whole bunch of random variables with just one algorithm for the uniform and just getting the inverse CDFs. So as a little example, we can actually look at some code here. Beyond the scope of this course to program in R, but if I generate, so here my first line, I'm generating 1,000 uniform UNIF 0, 1 random variables. Let's call them Y. And I could say, I could plot the density of Y. And it looks kind of uniform-ish, right? In 0, 1, I have a finite sample, so it's not going to be perfect, but it's kind of pretty flat. Basically like uniform. Alternatively, I could generate a bunch of exponential 1, and I could look at, say, the density of this exponential 1. That looks kind of like what we'd expect our exponential density to look like. It goes up and it falls down. And I know that if I want to generate a bunch of if I want it, I can generate from the inverse CDF of the exponential 1 distribution, this negative log of 1 minus y. So you can just solve that problem. You know the CDF of exponentials, and I can tell you that, or you can derive that the inverse of that CDF is negative log of 1 minus. And if I were to plug those in my uniform random variables into this negative CDF, I could plot the density. And lo and behold, it looks a lot like an exponential. In fact, they are now exponentially distributed. So if I take originally I took my uniformly distributed ones, I plugged them into their CDF, and now they follow the density or the distribution of whatever that CDF or inverse CDF corresponds to. Okay, so that's transformations. I'm going to stop here. They're really an integral part of probability and statistics. Next lecture, we will look at two-dimensional random variables. We're going to start talking about bivariate random variables.